Hello ladies and gentlemen, welcome to my talk on information hiding in cyberphysical systems. This is joint work with Wojciech Mazurczyk and Georg Haas. Speaking about information hiding in cyberphysical systems, I first want to introduce you to two terms. Information hiding is an umbrella term that comprises subdisciplines such as steganography research, copyright marking and watermarking, anonymity and obfuscation. And cyberphysical systems are systems that are containing computation environments and interact with the physical environment, measure it, influence it, like a smart home that measures temperature and controls the heating in a room, for instance. When we combine information hiding with cyberphysical systems, then we basically apply techniques from information hiding to the CPS. For instance, we store secret data, hide it in a CPS in a smart home or in a wearable, or we try to perform copyright marking, maybe for the goal of preventing product piracy, but more on that later. First of all, and in chronological order, some related work. One earlier work by myself, together with Benjamin Kahler and Thomas Rist, was on smart building scenario identification for steganography application in the network of smart buildings. We embedded secret data in network transmissions, and we proposed a multi-level security-based protection approach. Tuk and Hales in 2015 proposed two new forms of covert channels that rely on modulation of transmission power and sensor data and persuasive computing. And in the same year, another approach for data leakage in CPS, also with a multi-level security based countermeasure, was proposed by Hauser. And finally, in 2016, Tonnage et al. Detected anomalies in building automation networks using the BACnet protocol using unsupervised machine learning methods. And these anomalies contained also two forms of covert communications. One was a timing channel and one was a storage channel that hides data in a way that unused fields of the protocol header were used to embed the secret data. That leads me to the question of what are actually our goals and what do we try to achieve with our paper. So we wanted to know how much data can we actually hide in a CPS and for how long. The possible benefits are that we were hoping for at least being able to store a cryptographic key in a building. That was the main purpose, because we were considering a smart home and other forms of CPS allocation where nobody will search for a cryptographic key. Further, we could use our research work for fighting product piracy. So if, for instance, one company engineers a product and wants to prevent that another company copies the product, then we could ensure that the product identifies itself or other components of the same vendor using some steganographically hidden data. To achieve our goal, we came up with two different strategies to store data in the CPS. One is the register strategy. We call it register strategy because we utilize unused memory registers of CPS components and then embed data in these components. And on the other hand, we have the actuator strategy. So actuators are the devices that control, they influence the environment. For instance, they open a window, close a window, open a door, or similar things. And while sensors would just measure the data, the environment, for instance, the temperature in a room. And we try to set the states of the actuators in a way that they won't be recognized by the stack analyst or by inhabitants of a building or in general users of the cyber-physical system. I will start with the register strategy. So in this strategy, we have the setup that we search in a CPS for a device that contains unused registers. Here we see a device A, it's a temperature sensor with 2 unused registers with 8-bit each, and we spread our secret data over both registers. It's likely that we need multiple devices, so we can just add more devices to it. Here it would be device B, and as also shown, we would just use an area, just 2 bits of a register, because maybe we cannot use the full register. Maybe just a few bits are unused. This approach is linked to a number of drawbacks. First of all, writing register values requires us to have a direct access usually to the CPS device, for instance over the local bus, one wire, or whatever bus system is used. And the register size is very limited. So we cannot store much data in one device, at least we cannot expect that. It will be very few bits per device. And obviously each device has different, each model has a different number of available registers, maybe 0 registers in some cases. And these registers are accessible in highly different ways. We have to look up for every device, e.g. in a data sheet, which registers are eventually unused. However, it also has some advantages. One advantage is that several CPS components can contain such unused registers. And sometimes a device with unused registers is deployed many times in the same CPS, so we apply the same data hiding approach and access technology to the device several times in the same CPS. We, for instance, use the temperature sensor that contains 2 unused registers or potentially unused registers, and it could be developed several times in the same CPS. We have a good writing and reading performance when writing and reading registers. And what is also interesting when we perform this register strategy based approach is that we can compare it later to the other approach, the actuator strategy that I mentioned earlier. So the question for us arose, which approach is actually better? The simple approach where we just write to the registers, or the approach where we modify set points, which is more sophisticated, but which approach is better? I will answer this question later. We performed some simple experiments first so that we have data to compare the register-based approach with the actuator-based approach. And for this, we used the Maxim Integrated Products DS18B20 temperature sensor. That's a sensor accessible using the one-wire protocol. And the approach was to store data in the alarm registers that are unused usually, and we combined up to 4 sensors. We sort our data as we split the data over separate sensors using the unique serial number of each device. And we can write and read the serial number over the bus connection. In our experiment, we performed 100 reading operations from 1, 2, and 4 sensors simultaneously, measured the average time per written value, and did something similar, also 100 operations for writing data in a loop, and so that we made sure that not the same data is written, and we just switch between 0, 0, 0 and 0xFFFF in a loop. So reading performance was very good. Writing performance also, we had 0 errors even when reading 180,000 values, and on average the reading performance even increased per sensor when we read more sensors, because the addresses of the sensors just had to be fetched once. So this is why the value for the average time consumption of reading 4 sensors is slightly lower than reading just 1 or 2 sensors. Writing took significantly longer, but was still in a range where we can say for a steganographic purpose it's a very good performance. However, this leads to the question of how much data we can store in a CPS this way. Of course, it highly depends on the number of deployed CPS devices and their available register space. So we select a subset of the devices that contain unused registers and are accessible to us, called here the selected devices, and we assume that it's about 4 to 8 bits per device that we can use. For 128-bit crypto key, we would already require 16 to 32 devices for storing it without any redundant coding. And for larger crypto keys, this would probably be infeasible in practice. This leads to the Actuator strategy, which is a little bit more complex. So we have a steganographer that sets a set point in an actuator. For instance, it sets the heating value to 80% of the maximum heating power for a selected heating device. However, this heater, as any other actuator, influences the environment in which it operates. In this case, for instance, a temperature sensor could measure the new temperature, and when the new temperature is registered, it's also either forwarded to controller, or maybe the controller pulse the temperature sensor on a regular basis. It depends on the architecture and the communication protocol, how it's done. And then the controller operates on the basis of some logic and rules that can be entered by the operator, and readjusts the heating value to the desired value, let's say 70%. And that's not the only problem we have, and problem because it overrides the value of the steganographer, so the hidden value is lost. The user, which could be an inhabitant or an employee working in a room, could also adjust the heating level. It could say, oh, it's too hot for me, I just decreased the heating level now, so he sets it maybe to 72%, and then the value is also overwritten. That means we cannot always use the full value here. We can only use a few bits of the value, like switching from the standard value that is maybe 80% to 82%. And for a steganalyst that tries to detect the steganographic operation that takes place here, he could monitor the temperature change or other changes of the environment and perform anomaly detection, and he can also act on the network level and try to detect anomalies in the network traffic. For instance, a steganographer could be a new network device appearing and sending a command to set the set point of the heater to a new value, and this itself would be an anomaly. There's, however, lots of related work available on such anomaly detection also in building automation networks. So what we did is we were inspired by scatter hoarding in the animal kingdom. Scatter hoarding is a strategy used by animals that collect food to store their food. And in summary, to summarize, it's basically that the food is collected and then spread over different locations called caches, in which food is hidden. And cache locations are determined in a way that they are unlikely to get detected by other competing animals, because the competing animals, if they would know where the food is, they would just steal it and eat it themselves or hide it in their own cache. However, by splitting the food over several storage locations or caches, the chance that a useful or a required number of caches to survive will remain. We did this in a similar way for our information hiding approach, and we call this adaptive information hiding. Adaptive methods in information hiding are not novel. They are used in other areas of information hiding as well. And our approach is to determine suitable actuators that we can use for data storage. We scan the devices of the CPS environment first. In BACnet, there is a network message that can be broadcasted, and then we know which devices are there. This even works for remote broadcasts and broadcasts to other subnets, so we don't need access to every subnet. And then we scan these devices to determine which BACnet objects and present values they have, and then we monitor their values. So what we do based on this information is, first of all, we exclude devices which are unsuitable to store data. For instance, a door opener. If we store data in a system that opens a door or a window, it's very easily recognizable, also by the human inhabitants, that there is something wrong. So this is not suitable for steganography or general for information hiding. And we also sort out devices with frequent status changes. So where the set point frequently changes, for instance, when a heater is constantly changing its set point based on a controller command, even if this change is not too big, it will still override our own set point. So the steganographer's set point is lost, and this means we have no embedded data left. This solution is not perfect. It's a first approach, but the steganographer operates on the assumption that the CPS historic behavior will be the same in the future. This is why we record data, and on this basis we sort out the unsuitable devices. But the future CPS behavior can change. For instance, if we have a smart building and we have an open house presentation day, then maybe some new rooms will be used or used in a different way. This will influence also the actuator's behavior. Or let's say a new employee moves into the building, gets a new office room that was previously unused, and now he influences the heater in that room, and we used that heater previously to store data. In that case, our data will be lost. So this requires error detecting and error correcting codes, such as parity bits. And for this reason, we need to spread our data in a redundant way over several CPS devices, similar to the register-based approach, where we also split our data over several devices. We performed experiments to determine how well we can actually store the data. And therefore we used the BACnet protocol. BACnet is an ISO standard, worldwide used, one of the most important standards in building automation. And the question was, how well can we store the steganographic data under different conditions? So how long will it last before it's overwritten? And in general, we wrote 100,000 values to an actuator. And in that case, it was accepting temperature values between 0 and 100 degrees. And we always incremented every new value. So we looped the values 0 to 100 degrees. And after each written value, we waited a time and then we read the current value to check whether it's still there. In the first experiment, we introduced the so-called spurious process. It's a process that influences the system. And in this case, a spurious process was just read-only and just read the same data either in a slow mode or in a faster mode or even in a burst mode. In none of the cases, our set value was influenced in a negative way. We read 100% accurate values because the BACnet protocol is reliable and can resend non-acknowledged packets. It can send the packets multiple times and then make sure that the set point is set. In a second experiment, we modified spurious process in a way that it also writes the data. So in this case, the spurious process represents the inhabitant or the control logic that changed the operator, the actuator state. Or in the analogy to the animal kingdom, it would represent a competing animal that tries to detect the hoarding location. That would be a read of the data and then steals the food. That means it replaces the value that was hidden with a random value. And our spurious process writes data every t seconds, while the desired storage time was s seconds. And we simulated situations that were highly spurious, so where the storage time is the same as the interval of the spurious process, but also situations in which the spurious intrusions were very few, so the storage time was much slower, smaller than the interval of the intrusion. Our results show that, of course, the storage time is one important factor, but the interval of the spurious process plays another very significant role. The question that underlies our experiments is how long is a realistic data storage and how long is the typical intrusion or value overwriting interval. And we can measure this in our adaptive technology because we know, based on historic values, how long the typical change of the actuator's value will be performed, and based on this frequency we can determine how good the storage location is. If we want to come down to 1% chance of value overriding, we have to make sure that the interval is very, very small in comparison to the storage time. Actually, it's in that case 0.015% of the time that is required for the storage. This is not too unlikely. If we have a good selection strategy of CPS components of actuators, then this is an approach that we can use. Overall, for storing a AES key with 128 bits, we need at least 18 actuators in this setup. And what we cannot use are Boolean operators. We need at least integer values. The more finer these values are grained, the better, because the smaller we can make our influence on the physical environment. These 18 actuators are very, very optimistic. This is only the case if we can store 7 bits per useful actuator. So that means in large or medium-sized, at least, building automation installations, where we can use 5 to 10% maybe of the actuators, we can store between 350 bits and 1.7 kilobits if 7 bits per device, per useful actuator device, can be stored. This is less efficient than the register-based approach on one hand, because we need more devices, but we also have an advantage, and that advantage is key here, because when we use a unified protocol such as BACnet, we have one technique that we use to store and read our data, while the register-based approach needs device model individual reading and writing strategies. And especially in larger CPS components, a unified protocol is then an advantage over a non-unified approach. The performance is very good in our virtualized environment. We use the BACnet IP stack. However, with real actuators and real bus systems, it's much slower than these 0.0055 seconds per reading and writing value. Actually, setting a value can take multiple seconds. We had also 0 errors with the read-only spurious process. So if actuators are selected without, which are not modified because they are maybe unused, then our data can be considered very robust. Again, these values, the number of actuators and bits per actuator, are not considering redundant coding. To conclude, the amount of data that we can store highly depends on the type of the CPS, on the method that we use, and the number of available actuators. And these factors also, in a similar way, influence the robustness of the embedded data. Our work has some limitations, and that is especially the structure, the environment, the capabilities of each CPS are different. A smart building is different from an industrial control system and from a wearable, and so we need further studies to study further CPS types. And also some CPS types, such as industrial control systems, are linked to a significant problem, because the cost influence of storing data there by modifying registers and especially actuator set points are not always clear. Actually, it's quite likely that it's very unclear to the steganographer what will happen if some values change. So it must be considered highly risky to write these new set points. In future work, we want to analyze novel approaches. For instance, we want to store data in the BACnet change of value subscription, so we don't store in actuator values or register values. Instead, in BACnet, one device can subscribe to a value change of another device. For instance, if it's a device A, can subscribe to a temperature sensor and tell the sensor, okay, if the value changes so and so, please inform me. And these relationships are stored and this is our approach, represent hidden information. So we don't change the system, but can represent data anyway. And we also want to explore the copyright marking further to see what a DRM for automated buildings especially can be a path to fight product piracy. So we need to find out how is it feasible in the best way and how efficient can it be in practice. All right, then thank you very much for your kind attention, and I am happy to answer your questions.